Well, thank you very much, Heinz. That was kind of a surprise. I'm not sure if that's real or not. But one thing before I start, just a personal note. I find that the older I get, the more time I spend on historical aspects. So about half of my talk is going to be history here, and then try to say some things in the second half about maybe the newest developments in the area of POPs. By way of introduction, the Bayreuth meeting in 1990, Olaf Paepke and several others that co-chaired that session. Chris Rappe had really laid the foundation, I think, for dioxin analysis prior to that meeting, but we really knew very little about human biomonitoring at that time. And so over that period of time since Bayreuth in 1990, we've really made tremendous progress in understanding what to measure, how to measure it, to do it in a very sensitive manner, and accurate manner. So over the period of time, there are some emerging issues that needed to be addressed, and they became clear over the decades. A need to go from an external to an internal dose measurement. Many times epidemiologic studies are using as their exposure index an external dose based on levels in the environment. And we now know that just measuring something in the soil, for example, or dust or water doesn't necessarily mean that it gets into the human body, or how much of it gets into the human body is not always what's in the environment. So the new biomonitoring approach to exposure assessment has really taken hold. What matrices could be used for POPs? Now there's all types of matrices that we use. Back then it was usually adipose tissue. Analytical method development for all the various matrices over the decades. Development of higher throughput methods for large-scale exposure assessment. And FMS, for as far as CDC is concerned, was instrumental in us being able to do large-scale epidemiologic studies because they're highly automated methods now. The need for real matrix standard reference materials, which NIST has quite a few of those now, and those are very important for accuracy and quality assessment. Large, comprehensive sets of analytical standards. Cambridge Isotopes, for example, that's a sponsor of this meeting, over the years has developed a whole set of analytical standards, both natives and C13s, that are vital to the accuracy of these methods, and lower detection limits. And over time, the levels have been dropping in humans, so it's become more and more important that we get more and more sensitive in being able to make measurements. One of the objectives of exposure assessment to environmental chemicals is the quantification of the magnitude, the duration, the frequency, and the routes of exposure. An example, measuring these in all of the various environmental media. And then what we really want is to characterize and enumerate the exposed population. There are two ways, as I said, to do that. One is the external dose measurement, which uses modeling to predict an internal dose. And then there's the internal dose measurement, a direct measurement of the internal dose of the chemical that we're interested in or its metabolite. The conventional approach, the indirect approach, uses questionnaire data, the measurement of the concentrations in the environmental media, and then there's assumptions made about media contact or intake routes, and that is used to yield an applied dose. One of the problems in predicting levels in people is a very, very complex situation. You have all these levels that we're exposed to in our environment, in our food. Nutritional status can play a role, lifestyle factors, personal habits, genetic factors, all of the absorption coefficients from the lung, intestine, and skin, for example, have to go into that. Many other factors in addition. And you put that into a model, and you come up with some predicted level of toxicants in people. The biomonitoring approach, on the other hand, provides the direct measure of exposure. It integrates all of the different pathways, though. You can't differentiate where it came from by what pathway, but it gives you an internal dose measurement. It does decrease the uncertainty inherent in exposure assessment by the conventional methods. It provides a more biologically relevant measure of true exposure. So it's an indicator of the internal dose. It provides exposure estimates that more directly relate to the concentration of the active agent at the target site or organ. So one message, if I would have one, that would come out of the introduction part is that instead of predicting, why don't we just measure the levels of the toxicants in people using biomonitoring? I want to give you a classic example of why this became clear many years ago, of why that was important. We all know about the Agent Orange herbicide that was sprayed as a defoliant. It's a mixture of 2,4,5-trichlorophenoxyacetic acid and 2,4-D and diesel oil. And at some point, it was determined that the 2,4,5-T was contaminated with 2,3,7,8-tetradioxin. This is the aircrafts called the Operation Ranch Hand that was used to spray the herbicide in Vietnam. And years ago, the Air Force was going to be conducting a large-scale health study of all of these ranch handers that served in Vietnam. And they needed an exposure index for their health study because it was going to cost many, many millions of dollars. And so the best epidemiologists in the world were gathered and came up with this ranch hand exposure index, which is along the x-axis here. And shortly after our paper was published on being able to measure these levels in serum, the Air Force came to us and asked if we would run some of their ranch hand veterans' serum for tetradioxin so they could validate their exposure index. So in this axis is the levels we found of 2,3,7,8 TCDD in these ranch hand Vietnam veterans. If you look at this, this is an absolute textbook worst case scenario for a study. The ones that the Air Force would have thought were their highly exposed individuals here actually had some of the lowest dioxin levels in their serum. And vice versa, those that they thought may have been low exposure had the highest levels in their serum. So it became very clear that this exposure index wasn't going to work. And in fact, if they had used that over the decades of the study, even if there were health effects associated with that exposure, they never would have found them because the misclassification was just too extremely large. What you really want is that data to lie along this dashed line. So this is just one example where it became clear that biomonitoring is going to be very important in doing health assessments. I want to use as examples here today of the persistent organic pollutants of tetradioxins and dioxin-like PCBs. Within the human body, the pharmacokinetics are that they have very high passive diffusion. They're distributed from the blood to the fat in adipose tissue and milk and other adipose tissue stores of the body. They're metabolized very slowly, and their excretion rate is slow, so they have a very long half-life. That's why they're considered persistent organic pollutants. Back when we first began our studies and wanted to know if we could measure dioxin in Vietnam veterans that had been back from the war for many decades now, could we still see an elevation in their blood if they actually had an elevation? And in the literature, if you went and looked, you would find all of these half-lives listed for various animal species here. And the half-life here is very, very short, and even in the monkey. And looking at that data, you would think that there was no way that we could look at exposure decades after the exposure ceased. But it turns out, doing studies with the Air Force and with Seveso, Italy, that the half-life in people is considerably longer than any of these animal species. So it does provide a measure of past exposure to, in this case, dioxin. There's a range of half-lives, however. In this nice paper, the dioxins and furans are listed along here, and the various half-lives that have been measured are shown here. And as you can see, there's a range of half-lives for tetradioxin and penta, some of these going up close to 20 years in half-life. And some of the others are shorter, but they're still all on the order of years. If there's anybody here that doesn't know what dioxin is, I threw in a slide here just to show the structure of dioxin. There's 1 to 8 chlorines can be put on this nucleus, so there's 75 different congeners. There are 135 different dibenzofurans and 209 different PCBs. And they are very similar structures, just differ by oxygen atoms attaching the benzene rings. This is the 75 chlorinated dioxins, all shown on this slide. And Not all of these are considered toxic to animal species. So what has happened is regulators and toxicologists like to have a single number to work with rather than 75 or 135 or 209 numbers. So there's been a lot of tests done, various endpoint tests on these various congeners to decide on which ones are really important from a toxicologic point of view. And these are the 7 dioxins that are of interest, and they all have this 2, 3, 7, 8 position substituted by chlorines. Some of these others have additional chlorines on them, but as long as the 2, 3, 7, 8 position is substituted, they have some toxicity in animals. So this toxic equivalency concept is the toxicity of the dioxin-like chemicals vary, and the toxic equivalency factors that have been assigned for all of these compounds, you multiply the concentration you measure for each of these by this TEF value and sum them together, and you get what's called the toxic equivalency for that person, for these 29 chemicals in this particular case. And that's what is used and reported most often. Just to show you one little slide of what the TEFs are, 2378 TCDD is assigned the value of 1, and the pentadioxin is also assigned 1, and then the others are various fractions of TCDD or pentadioxin. Just a quick few summaries about POPs. They're ubiquitous environmental contaminants. They are higher in industrialized societies. They're lipophilic compounds, so they're found in all the lipid stores of our body. They're distributed equally in the lipid stores around the body, and they do increase with age. And this just kind of shows you that this is adipose tissue taken from various parts of the body, and this is the dioxins that were measured here, the levels. And for the most part, they're about the same as long as you correct for the lipid content of the matrix. There's a slight elevation for tissues around the heart, for example, but it's not statistically significantly different. We wanted to switch from adipose tissue to serum at one point in our laboratory method development, and so we had to validate that. And this is the adipose tissue levels and the serum levels measured in the same individuals that had levels almost over 3 orders of magnitude. And we were able to get that from the Missouri Times Beach study individuals. And as you can see, this is really almost unbelievable correlation between adipose tissue and serum on a lipid-adjusted basis. So it validated that we could substitute adipose tissue for serum, which was a much easier matrix to get for our studies, less invasive. The serum dioxin levels are increased with age, we know now, and the older we are, the higher the levels of the dioxins and other POPs are in our tissues, and that's probably because years ago, those of us that are older lived during the time whenever these levels were at their peak in the environment, and so we're still offloading those compared to younger individuals. They bioaccumulate up the food chain, and that's how we get most of our exposure. We can measure them in the lipid stores of the body. It's primarily through food of animal origin, about 95% of our exposures nowadays. And the human levels are declining. And so that kind of leads into what I'm going to be saying at the last part of my talk is this with me, it's a quest to always get to more and more sensitive analytical techniques. And so I'll just describe that a little bit. Blood is about 0.6% lipid, mother's milk 3 to 4%, adipose tissue 95%. So this caused some analytical challenges in going from adipose tissue to blood. I want to say just a few words here about this analytical measurement process in human samples. It requires very selective sample preparation. We've used FMS automated equipment my whole career at CDC, and it is automated, so it does allow for high throughput. High resolution mass spectrometry, and they're somewhat expensive, so it does cost money to acquire and maintain high resolution mass specs. Isotope dilution quantification and isotope standards are expensive as well. And then the results are reported on a lipid content of the sample. So it's not a cheap analysis to do a human biological measurement for POPs. Human nature being what it is, years ago at CDC, there were no analytical standards. Back before CIL made analytical standards, we needed all of the native dioxins, furans, and PCBs. We needed all of the carbon-13 labeled dioxins, furans, and PCBs. And since they weren't available, we had to make them ourselves in the laboratory. So we did construct a chemical toxicant laboratory that did cost a lot of money. We were able to synthesize most of all the standards that we needed in a very safe manner in multi-milligram amounts. And some of you know that TCDD, for example, is exquisitely toxic in the guinea pig. And so it was done in a very safe manner. To show you why isotope dilution is needed for accurate quantification, this is a particular furan, the 23478 substituted furan. This is in spiked recovery experiments, what we expected to find on this axis after going through the entire method, what we actually found on this axis. And this line is not the linear regression line, but it's the one-to-one line of what we would expect for good quantification. As you can see, having the isotope for this particular furan in the method provides tremendous accuracy. This is another congener that we did not have a C13 for at the time of the analysis, and you can see it's all over the place here. It's not really good, accurate quantification, and so because of that, we use isotopes of the compounds for most everything that's done, did do at CDC. I'm no longer there, and I apologize, I keep reverting into that we, but since I've retired from there, it's not me anymore. Some major challenges in measuring dioxins. You need extensive quality assurance program because you want to make sure it's the correct congener because they're not all equally toxic. You got to be sure that the amount that measured is correct, so it does require long-term quality control, and this is just one example to show you a chart for TCDD from 1985 to 1990. The mean here is about 1.6 parts per trillion level, and these QC materials are inserted in all the analytical runs and run along with the unknowns, and the QC has to meet certain criteria in order to report the results of the study. I put a blank in here just in case anybody has a queasy stomach. I'm just going to show 3 slides of how we began the analysis using adipose tissue. They're not very bad, but if somebody doesn't want to look, I just like to warn you ahead of time. Back when we began, we would ask a plastic surgeon if he wanted to volunteer for our study to come in and make an incision and withdraw the sample, and this is about the size sample that we needed with the sensitivity of the instruments back in those days. Then after sewing up that area, you were left with this great big dimple in your stomach. And so because of that, we had a very low participation rate in our first study, which was Times Beach, Missouri. If anybody's familiar with Times Beach, that was a town that was completely contaminated by spraying oil that was contaminated with dioxin for dust control. The U.S. federal government ended up buying the entire town and moving everybody out. Everybody had to leave their cars, their clothes, all their personal items, and just get up and walk out the door, never to go back again. And we needed controls for that study. And so we really tried hard to get people to volunteer. And because of that low participation rate, that led to us looking at serum and changing our method to serum. All persons from industrialized societies have dioxins, furans, and PCBs in their bodies, so we all know that. We all have them. Therefore, before what is abnormal can be determined, we need to know what normal is. We have to define what normal is, since everybody has these compounds. So if you want to say you've been highly exposed to dioxins or PCBs or PCDFs, you've got to know what the baseline is. CDC has the National Report on Human Exposure to Environmental Chemicals. It's an ongoing every 2-year biomonitoring assessment of the U.S. population to selected chemicals, and they use urine and blood and some of its components for these various measurements. This is the 4th report, the last report that came out in a hard copy anyway, and this is just the chemicals that are in that report, over 265 chemicals from all different classes that you probably all recognize. Many are new and emerging environmental contaminants of concern. A lot of others are historical ones like dioxins, PCBs. But this is an absolute treasure trove of information. It's all available for free out there on the internet, on the web. You can go to the website, and many researchers around the world are using this data now to look at all different aspects of exposure to these chemicals. I'll just show you 2 or 3 quick examples of the utility of it for epidemiologists. For example, para-DDE, which is the metabolite of DDT. All of us still have that metabolite in our bodies, even young individuals. But if you look at this, let's look at Mexican Americans, 60 years old and older. If you look here, the levels in the males and females, a huge difference between males and females. Why is that? That's something an epidemiologist might be interested in following up, is why is that, and what impact is that having on a person's health, for example. We see the same kind of thing in non-Hispanic blacks and non-Hispanic whites. It's not quite so evident that there's a difference between males and females. PFOS, which is a new contaminant, the PFCs, that everybody's concerned about. This is from pools from 2001, 2002, NHANES. But just a very interesting thing that someone would want to follow up on if you look at this. These are the young children, 3 to 5, 6 to 11-year-olds. The children from Mexican Americans have much higher levels than the adults. Same thing for non-Hispanic blacks, and it still is true for non-Hispanic whites, but it's not quite as pronounced. There are differences between men and women as well. I'm going to skip these. So beyond NHANES, in utero and early childhood exposure, the most susceptible life stages, how do we assess their exposure? So that's a new area that people are looking at because it's very difficult to get samples from very young individuals, for example. Very young children and babies, we need improvements in sensitivity to be able to measure them. Finger sticks, blood spots off of finger sticks would be nice if we could have the sensitivity to be able to measure that instead of taking 5 red tops of 50 mils of whole blood to get 20 mils of serum. That's a lot, and you can't do that in young children. Elderly people, it's difficult to get, or people who are sick. So driving all of this is sensitivity. If we can increase our sensitivity, we can decrease the amount of matrix that we need to do these analyses. We know that 95% of our exposures through our food. We've had a decline of 80 to 90% in our dietary intake of these compounds since 1980. So that's another thing driving this need for increase in sensitivity. The background levels have been declining, and their measurements is becoming increasingly difficult. So the sample sizes required have been increasing instead of decreasing. So one of the things we need to do is take a harder look at sensitivity. I should say here, there's a very practical reason, even aside from that, that always pushing your sensitivity is important in epidemiologic studies. These are power contours versus the number of samples that you need to get a certain power in your study to tell the difference between 2 populations, for example. The standard deviation of the analytical measurement process is directly involved in this, D term. So the lower this is, the higher the D is. So in this particular case, if you have a D of this level and you want this power, it requires this number of samples to be run in your study. But if you had a higher D and you wanted to keep the same power, you could reduce the numbers of samples and save a lot of money in your study, and vice versa. You could go to higher power, keeping the same number of individuals. So there's a very practical aspect to increasing your sensitivity of your analysis. So there's some new things being done in that area. I'm going to have one slide on 2 of these, and then I'm going to spend the last part of my time talking about this new timed cryozone compression method being worked on at Thermo. There's GC-GC with high-res mass spec, GC-GC with time-of-flight mass spec as well. And this GC-GC concept has some advantages. It has increased peak capacity, But one of the secondary features is you get increased sensitivity. So basically what it is instead of having a one-dimensional separation, you have a two-dimensional separation with some kind of a modulation system in between the first and second dimension that you can modulate what's coming off the first column into the second column. And that allows you to have a 3D plot. Instead of a peak area, you could look at peak volume now. And these are the two separations here. If you looked at just a one-dimensional separation in this little cartoon along this line right here, there'd be one single peak, but there may be 2 or 3 or 4 things under there that you don't even know is there. So this new technique has the capability of, and I think others may be talking a little bit about that later today, having the ability to find things that you didn't really know were there. But because you're reconcentrating the sample here and injecting on a shorter column, you can compress the sample and you get a better signal to noise, and I'll show that a little bit later. Just an example of what this can do using a loop modulator, and I don't have time to go into all the aspects of the different modulation processes, but this is 1 femtogram on column of 2378 TCDD, looking at the 322 ion accurate mass at 10,000 resolution. And you just take a look at that peak, signal noise of 1400 over 1400 to 1 on 1 femtogram of material using this GC with the loop modulator. That's kind of what really piqued our interest in this technology, that it really could work. And I'm going to show you where we're at in this toward the end of this talk. And there's still a lot of work to do, obviously, but it has great potential. This gives you the aspect of the three-dimensional nature of this. This is 313 attograms of TCDD with a signal noise of greater than 400 to 1. And you can see this is really a peak volume and not a peak area anymore. One slide showing the time of flight as the mass spec instead of a high-resolution mass spectrometer. This allows in a single injection to be able to measure all of the pesticides, the persistent pesticides, PCBs, PBDEs that are found in our adipose tissue as of today. And they're all shown here, about 59 analytes. They're all separated out now by GC retention time, or there's still several, even after 2 dimensions of separation, that are still co-eluting here, but these two have different masses. It's a time of flight mass spec. You have the full mass spectrum for each compound, so you can pick out the masses that pick these apart and quantify them. And there's the papers that have been published on this by Jeff Volkant, looking at these, all of these in serum and in breast milk, using this technique. The final part of my talk is this new approach, timed cryozone compression. I do want to acknowledge here at the beginning the people who are working on this, Heinz and Dirk. Heinz is here, and Dirk and Kyle from Thermo, Jeff Volkant from the University of Liège, and Andreas and Wayman Turner from CDC. This paper came out in 2011, which was a concept of could this possibly work. So it was a concept paper, it took the entire peak and cryo-trapped it in one single event. And what you'd like to be able to do is do it in a timed fashion where you can trap or not trap if you don't need the extra sensitivity. So there's a paper out by Thermo, and you can see it here. If you go to this website, you can get the paper talking about this concept of time-controlled cryogenic zone compression. This is done on a DFS, high-resolution mass spectrometer. This just shows the normal 20 femtogram signal to noise on this particular instrument. This concept and the basic effect of GC and what it does. This is a peak here for PCB 77 without the modulation. This is the refocused GC peak after modulation, and they're overlaid here so you can see the big increase that you get in signal to noise using this technique. The basic concept again is one column in a particular case with a modulation, or in this case a CO2 jet cooling point between the column near the end of it, about 4 meters of it before it goes into the mass spectrometer. And the cold jet is turned on at a certain point to trap the peak. And this just is a picture of the cold jet. It's one jet system. And so without it turned on, your normal peak here, if with its retention time, if you wait until it gets close to this region here and you turn on the jet and you trap it, and then you turn it off and re-inject it, you get a much narrower peak and an increase in signal to noise using the technique. So to show how this would work with a standard, this is the dioxins, furans, and coplanar PCBs that we normally see in all adipose tissue samples. This is a standard injected here. Now, if we need more sensitivity for 2378 TCDD, for example, as it's going along, we turn on the modulation process. You can see the big increase in that peak right there. You can do it here for the 23478 pentafuran and the 12378 pentadioxin. They're both turned on for both of those peaks, and they're left off for the other peaks. So you can use it just whenever you need it. We had a set of analytical standards created that went to very, very low levels so that we could take a look at the instrument LOQ and try to see how low could we go. So this is kind of like doing the limbo, and I want to show you here the first peak, this 5 femtogram per microliter, and I believe this is injecting 4 microliters on there, so that's really 20 femtograms, gives a signal like that. 2 femtograms standard, injecting 4 microliters, gives that signal. 1 femtogram, 500 attograms standard. In that case, that would be 2 femtograms on column. And then 200 attogram standard, that's 800 attograms injected, still gives a nice signal. So the question is, and where we're working is, how low can we really go here? Can we cut back on how much we're actually injecting and look at the instrument LOQ anyway? And what lies below here? Of course, the big issue is going to be the blanks. Blanks are going to end up being the limiting factor because we're down now in the point where we're pretty close to being able to see everything and everything, I think. And so blanks are going to be a big issue if we're going to be able to develop this method into a method that can be used routinely in human biomonitoring. This just shows you a standard curve for 2378 TCDD. This is the area that we're really concentrating on down here. This is 800 attograms absolute on column down to this point right here, but it's still a fairly good standard curve. So the concept is that it does work. We just have a lot of work to do yet to make it viable. I want to show you a couple of last slides here for pooled blood sample for TCDD. Without using the cryofocusing and with using it for TCDD, you can see the 2 peaks here. The signal noise is about 16 to 1, and this is an actual blood sample now with a real matrix. You can see the signal noise, big increase to 273 to 1 using the cryofocusing. Just to show you, it's not just TCDD. This is one of the pentadibenzofuran 23478. And we get the same kind of tremendous sensitivity increase in a real blood matrix. So there is a clear gain in sensitivity from the technique. The combination of this time-controlled cryogenic zone compression and standard measurement is possible. You don't need to use it when you don't need it. There's a free choice of analytes to be cryofocused. You can pick out which ones in your chromatogram you want to do. Switching from normal to the CZC without any hardware change. There's no special software needed for the chromatograms nor the quantification. It's a very low CO2 consumption compared to normal GC, which I didn't have time to go into. and the use of standard columns. There's still a lot of work to be done, so I don't want to leave the impression that this is a method that people can take to the laboratory right now. Ion statistics and ion ratios, when we're getting down to those very, very low levels, if you look at the overall transmission in a mass spectrometer, the number of ions actually getting the detector is very, very low. The repeatability needs to be looked at. The LODs in real matrix have to be better defined. There's hardware, software, blank issues. The ruggedness for large studies, scan speeds and dwell times, and there are many, many other things that I could mention that need to be worked on to develop this method. So where are we right now on the scheme of things? Well, 1 femtogram of dioxin is still about 2 million dioxin molecules. And 1 femtogram sounds like a very tiny amount, but it's 2 million dioxin molecules. The 313 attogram chромatogram that I showed you is about 500,000 dioxin molecules. I think we can go lower than that, but where and how low, I don't know. But one day we'll reach this phantomal range. The important thing is, though, right now, how important is 500,000 dioxin molecules from a human health perspective? Toxicologists and risk assessors are going to have to tell us how important that is, and that will dictate how low should we really go. When is low enough? When should we stop analytically?